very conscious of the speakers that have gone ahead of me, and I'm very grateful to the sponsors of the lecture for this invitation as well, and to you. I thought it would make sense if I constructed this lecture really in a sort of high-level fashion. I chose that brief because I thought it would be of most interest really to the audience. I hope I've got that right. It also more accurately reflects my personal contribution to the work, especially in the more recent work. And that naturally leads me to want to acknowledge my co-workers right at the very start. These are the colleagues who did the nitty-gritty work, so to speak. And also to acknowledge at the very beginning the research partners that I've been very, very fortunate to work with over the years. And you will see from the examples that I'm hoping to show this afternoon, or this morning in your case, the work of numerous partners. Finally, the presentation is a bit of a journey through my research career, with the most recent work being presented at the end of this, towards the end of the lecture. So my focus has always been, and my interest has been more on the environmental side, and worked, as was already said, in setting up the Geoenvironmental Research Centre. We're here in Cardiff, in Wales, and I will start with a very nice picture of the environment, which is of a reservoir about 60 or 70 miles north of Cardiff. It's quite near to my hometown, actually. And that reservoir is man-made. It's held there in place by that wall that you see in front of you, that I'm showing just there, pointing to just there. And if we do a cross-section through that, then that's what you get to see. That is called the Llymbrianne. And you can see the traditional picture of the clay core and the reservoir, the dam itself that contains and holds back that reservoir. Obviously, the function of the clay core is well known. It's to manage the flow of the water through in a controlled manner. And that sort of leads me, I hope, to be able to talk a little bit about the kind of things that I've been interested in. That example is as important as it is, and it's hugely important, of a large reservoir and a large rockfill dam. That is one flow pattern. That's the flow of the water through the dam. I've been interested in those processes, the ways in which things flow through soil from the very start of my career, really, and starting with heat flows, combining heat and moisture flows, and then building that to then go a little further to include chemical processes. And the purpose of this slide really is just to illustrate the sort of, greater level of complexity that you get to as, those problems increase in the number of dimensions and so on. I hope that slide speaks for itself these days. This is a pretty well established now areas of research, with many people around the world interested in exploring these coupled processes. My work, my center's work, are described here in one slide. The overall approach we've always tried to develop is to attempt to capture the physical or the physical, the thermophysical or the physical-chemical behavior in a theoretical formulation. Some of this is easier said than done, but this sets out the pattern of what we've been always tried to do. We've always followed a mechanistic approach, and I do want to highlight that is what we've done, is a mechanistic approach, as opposed to what is arguably a more rigorous theoretical sort of irreversible thermodynamics approach. But the mechanistic approach is sort of an applied approach, if you like. The work involves multi-phase and multi-component models. primary variables of temperature, water pressure, another suction, gas pressure, deformations, and chemical concentrations. And I've included one formula, as you can see there, which is kind of a coupled formula for one of the phases. We then take that forward, as many people do, to produce numerical solutions of those equations, the coupled equations, in the main, using our software. Numerical solution techniques we've always used is the finite element method, and we've spent a lot of time developing our own in-house software, which I call their robust software, to solve the problem. Our code is codenamed Compass. In the sort of later stages of the work, we've also needed to use other codes to couple into or to hop into to be able to do some of the reactions, the chemical reactions, and so on. But I won't go into great detail with that. That is one slide that in many ways describes, the years and years of research work that I've been carrying out. But I think hopefully it's kind of gets the message across to you about the patterns in which the kind of the strategy, the ways in which we've been doing our work. So having said that, I thought it would be of greater interest to you as the audience this morning if I said a little bit more about these application areas that I've worked on and some of the conclusions, some of the interesting things that have come out from that. And I wanted to start with the problem of high-level nuclear waste disposal, which is certainly still a very significant, internationally important, high-level in its own right problem. I think fair to say that a huge amount of work has been done and a huge amount of research has been carried out, and a great deal of really excellent progress has been made in the overall study of this problem. Certainly not claiming all of that carried out by us at Cardiff, but it's been a very comprehensive international program of work that I and the team have been very fortunate to be involved in. This schematic here shows, in essence, the type of problem that we have been working on along with others. So on the left-hand side, you see the canister being represented. That is the radioactive waste canister. Because it's high-level nuclear waste, it generates heat. So that's the hot canister at that end. That's the elevated temperature. And on the right-hand side of the slide, you see the host rock being shown. And between the two, the buffer material is installed. The conventional approach that became very well established was to use bentonite to, highly compacted bentonite actually as that material. And all the boxes that you see then just try to describe, the various phenomena that are at play. So obviously from hot to cold, you have heat transfer starting on the left-hand side. Because it's an unsaturated material, it's an unsaturated clay buffer, you do have vapor and airflow due to the elevated temperature. You get a certain amount of thermal expansion of the clay. You get thermal diffusion of chemicals. You also can have accumulation of chemicals due to precipitation at high temperature as the water comes back towards the hot canister. The idea of the host rock is that apart from, or one part of the idea of the host rock is that it actually supplies the water that will resaturate the clay buffer. So you have water flow back into the buffer, looking now at the right-hand side, looking at the arrows, the boxes down the right-hand side, you have water uptake due to pressure gradient. You have phenomenon of vapor condensation and return in liquid form due to moisture gradient. You have swelling pressure due to saturation at the cold end. Chemical inflow due to advection and diffusion, dissolution of minerals due to the dilution. So in other words, there's a lot going on. There are many complex processes that we need to, certainly when I was starting my work, we needed to do a fair bit of work to improve our understanding of it. High-level nuclear waste is a very interesting, I'd use that word in inverted commas, problem to work on. I'm using a slide that I was given many years ago by Neil Chapman, who used to work on the UK program. I'm very grateful to him for that. We highlights the time side. We waste disposal people, geoenvironmental people, just waste disposal in the ground. We maybe have to deal with numerous materials that are, not the most pleasant materials in the world to deal with. But I think the thing that I want to stress about this slide is just what's most unique, or is unique, about the nuclear waste program is the length of time involved. So this is gives you the sort of time scale that is being considered. And if you could see the horizontal axis, that at the bottom, that goes up to about 1 million years. And then some, again, after Neil, some sort of general breakdown of, the length of time is likely to take for various phenomena to take place. So, breakdown of the engineered barriers, region 1 eventually after about over 1,000 years, 3,000-4,000, and so on as you go across the slide from left to right. And what is I thought very interesting was to compare that, which again is what Neil did, compare that with the time with which we normally would be thinking about things, and that is the first 300 to 500 years, then half of today's European countries did not exist, before that time scale. The 5,000 year, which is the possible steel container lifetime, that is the whole of recorded history. And I think if you go further on, you can see how extraordinary some of these timescales really are. So this takes us into areas of consideration that, or should we say, that is certainly not the normal remit of civil engineers and civil engineering. Deep geological disposal is therefore, I think I can say, the leading emerges from that thinking really as the sensible solution to the problem, with stable geology being a huge and important requirement in order for those kinds of timescales to be considered and accommodated in the work. This diagram shows conceptual design of the Swedish repository, the SKB as it was at the time, with the idea being that the waste will be disposed in canisters, in a tunnel sequence at some depth to be determined in a stable rock environment. The exact rock type also to be determined, but this is the concept that is shown there. So you can see a whole series of tunnels basically with those boreholes drilled in the tunnels where the waste will be deposited. And then the blow up is a schematic blow up of that, so you can again see in a bit more detail the tunnel, and then the boreholes drilled in the tunnel, the container, nuclear waste container, high-level nuclear container exposed in that near borehole, and the buffer container material packed in around it. And there's a lot in there that is of importance and of interest, but that's the conceptual design of the Swedish repository. The work that we did, I've already said, comes from a mechanistic approach. So validation work is really, really important. It's always important, but for the mechanistic approach, it is kind of the vital importance. And we were fortunate to be involved in extensive validation work in this area over a 20-year time scale at varying scales. So these range from small-scale experiments in sands to start with, without any swelling at all, without deformations, in clays, in highly swelling clays, in so-called mock-up tests, which are large-scale, kind of size of a room type tests that produce very, very valuable and interesting results, have the advantage of removing the outer boundary condition, and then large-scale experiments in underground research laboratories. I'd like to say a little bit more about the work on the underground research laboratory. Time sort of prevents me from going into all the details of all the validation work that was carried out. But these are major laboratories that were established by various organizations around the world. This one is the Swedish Aspo Hard Rock Laboratory. And essentially, it's a tunnel approximately 3,600 meters long, which descends to a depth of approximately 460 meters. You can drive down it or go down in a shaft. And at various locations, there are research areas located where experiments are carried out. So I don't know that I've ever seen or known the exact price tag for a research laboratory of this size, but you can imagine this is not a minor sort of infrastructure. And each experiment within that laboratory would in itself be a multi-million euro, multi-million pound experiment. Right at the bottom of the, if I just go back, right at the bottom of that hazy sort of area here, some years ago, a so-called prototype repository, which was a third-generation full-scale experiment, was designed and built by SKB and partners, and I show you a picture of that there. We were fortunate to be one of the modeling teams. There were others, of course, that were involved in developing models and comparing our modeling results to the physical results from the experiment. And I thought it might be of interest to you if I just showed you a little bit of that. It is a complex geometry. It required full three-dimensional representation of the prototype repository. It incorporated all the primary features. The rock is faulted, so it certainly required a detailed specification. That's the full 3D geometric mesh that we used. And then some of the thermal results for section 1 as the temperature increases. The temperature results are important because they decide on the specification for the specification is decided for the maximum temperature that's permissible in the repository, and that then decides, in effect, and governs the spacing of the boreholes. And the spacing of the boreholes then in turn governs the kind of the geometry, the volumes, etc., of materials that can be accommodated in the tunnels, or put it another way, the length of tunnels that are needed to accommodate the volume of material that is to be disposed. So that's thermal results. And then you can see here for this one, if you look carefully on the one on the left-hand side, some very different patterns of hydraulic behavior to to the others, and all of that is illustrating that the hydraulic flow was very non-homogeneous, with fractures in the one area on the left-hand side allowing a lot of water in, and one of the boreholes actually being completely dry and the others being a little bit more uniform. That's to illustrate the importance really of the three-dimensionality, if you like. So to kind of conclude a little bit from that work, this is a major full-scale 20-year experiment, kind of third generation, hugely valuable, I would have said, in the development of the safety case, and yielded some very, very interesting results indeed. And I know that at the time SKB accommodated a great deal of that, if not all of that work in the development of their safety case. I thought I would just add another example, partly because I'm talking to a North American audience, but also because of interest in its own right. And there's some interesting, more recent research developments, although still these days, a few years ago now, on macro behavior of clay, looking at the physical chemical potential for these flows. And I want to talk now about an experiment that was carried out at another underground research laboratory, and this time it's the Canadian Underground Research Laboratory. So I'll take you a little bit north of, or good way north of Florida. This was situated in the province of Manitoba, which is right in there in the middle of Canada. Gets quite cold in winter, as you probably know. ACL, Atomic Energy Canada Limited, set up major laboratory, including a major underground research laboratory near Whiteshell Provincial Park, which was a couple of hours drive north of Winnipeg in the province of Manitoba. So some schematics there of the underground research laboratory. It was constructed in the granitic batholith known as the Lac du Bonnet batholith. Granitic rock is represented with an intrusive igneous hard rock found throughout the Canadian Shield. And again, that diagram there hopefully shows you the kind of structures that existed in the in the underground research laboratory. So it was 2 levels, 240 meters and at 420 meters. And each level had a lot of experiments being designed and carried out at that level. Now, I'm having to use the past tense to describe all of this because this does not exist anymore. This has actually now been closed. The whole laboratory has been closed, and it's no longer in existence. But draw your attention to this level. This is the 240 level. This is this diagram here. This arrow here points towards the so-called buffer container experiment in room 213 that was designed and carried out by ACL. That was the sort of I think it's fair to say that was the focus of attention, really, in order to get a better understanding of thermo-hydromechanical behavior. So that was a sophisticated test that took a lot of planning and a lot of designing. There was another test installed in this area, the isothermal test in room 205, as it was called. It was called the isothermal test, largely, I think, because it just didn't have the heating elements included in it. And it was a relatively, simple test. If you could describe anything in an undergraduate research laboratory as relatively simple test compared to the buffer container experiment. I don't want to give you the impression that it was a bit of a throwaway test, something that they just thought of, just like might be a good idea to do that, because I don't think that's true. It was well thought through and so on and so forth. This is a schematic that shows you the test, basically, and in essence, very straightforward. Borehole in room 205 at this buffer installed at this level, concrete plug, and sealed. Extensively instrumented, and information available for pre-placement, during the experiment, and after. So as one of the modeling teams that worked with ACL, again, I hope we just mention very strongly just how much work is carried out by others, for modeling teams like ourselves to be able to do our work is quite fantastic. we were working with ACL to predict, if you like, examine, think about this experiment from its early days. We weren't the only modeling team, but we were in the mix with them from day one, so to speak. It was intended to be a relatively sort of short-lived experiment. I just highlight here that, in fact, it lasted for 7 years. It was kind of, again, if I say it was left in the ground for 7 years, I don't want to give you the impression that it was abandoned or anything like that, but it was in the ground for 7 years. And the reason for that was not planned, not a strategic decision, but it was financial, basically. There was a bit of a downturn in the finances, and so it was left in situ for longer than originally planned. But eventually there were funds available to remove it and to decommission it. And that work was carried out in 2000. And this diagram attempts to show really some of the information that came out of it. And that was that if you look at cast your eye around these diagrams, and look at the scale, the picture scale on the right-hand side, you can see the greenish zones represent the areas that had resaturated or had begun to resaturate. And it's quite striking, isn't it, that layers B, D, F, G, and H, it's really just the very outer zone that's picked up water. Layer H is the bottom layer, so that it's much more sort of uniform across the layer because the water is seeped in from underneath. So and each layer is, I'm going into too many details, it's just a section through each of these, through the borehole. So that was interesting. If you compared, so there's another way of looking at it is a section through layer C. So the experimental results are shown there. And again, these now describe what I've just shown you from the previous slide, really, that on the outer edges here, which is in this region here, that then you have this increase in water content. This is the original moisture content here. And these are the numerical results based on best available information and material parameters and so on. And the timescale for full saturation or to reach this level would have been much less than the timescale that we were now looking at, the 7 years. So that was a very interesting lesson, I think, from this full-scale experiment. In terms of the complexity of some of this nuclear waste experiment, this is a relatively straightforward experiment. And if you look at and interpret it in terms of, the physical chemical structure of bentonite, then you can come up with a hypothesis for sure that, as the water is absorbed into the layers and the repeating unit layers of the bentonite, there's an expansion that takes place, and then that acts to sort of reduce the permeability, hydraulic conductivity of the larger pores. So it's a micro-macro interaction problem with, at the heart of it, the interesting kind of idea that you've got this flow taking place from the micro to the macro pores, and how you can model and how you can best describe the sort of the pressures that make those flows take place, and also the rates at which the flows will take place. So if we accommodate that thinking in a very, very basic way, and that is to sort of, instead of just having a hydraulic conductivity curve that the traditional manner, improves as the moisture content improves or increases in value, we modify that to take into account some of this kind of choking off of the pores. And you can see from the results there that we begin to be able to describe the pattern of behavior. Now, I'm not advocating that these hydraulic conductivity curves, the modified ones, are truly the right way to represent this in any way, shape, or form. But this is the first kind of guess, first stab really, as illustrating that the kind of thing that we were seeing did make sense, in the sense that, it could describe this behavior. So the conclusions really from this example, I would say, is that the pattern of behavior was one of restricted flow into the borehole. That we're talking about highlighting the micro-macro behavior of the clay barriers, the importance of that, and accommodating the fact the expansion of the microstructure tends to reduce the void spaces in the macrostructure as the material was constrained from swelling. I should have mentioned that, of course, this is a constrained picture. And, because this is all packed into the tightly into the borehole in high density into the borehole surrounded by rock. I did feel that these effects may be significant when considering the overall performance of a nuclear waste disposal repository. What I thought was interesting at the time was that, the amount of water that is available in this full-scale experiment, and just to repeat, this is, at the time, was quite surprising in a way, because this had been in the ground for so long, was it's the fact that the amount of water that the bentonite can take is decided upon really by the amount of water that the rock has available to provide it with. And because that amount of water was restricted, as it says there, the residence time of the water in the outer boundaries was high, if you like, then allowing time for this flow from the micro to the macro, from the macro to the micro, to take place, and then allowing the swelling to take place, so that then when more water was becoming available, then the macro structure at macropause had closed down, and it wasn't actually possible and possible for the water to flow any further in, and it had in effect practically sealed the outer boundaries. Of course, as with many things in research, when you see something like that happening, with your own eyes, if you like, from the results, then it's obvious, isn't it, that would happen, and B, you then start to scour the literature and you find that others have been there before you and have been saying that this is the sort of thing that would happen. But I still found it very interesting that it was kind of revealed in this way in this kind of full-scale experiment. So, current position on the nuclear waste disposal world is hopefully moving from R&D to operation. That was the thinking quite some time ago, actually. So I'm saying hopefully, yes, that's the case. As our host said, I was involved with the International Atomic Energy Agency work for quite a long time, and it is quite a difficult area to make progress, worldwide in. So many countries do find it difficult to take this agenda forward for very legitimate, not necessarily technical, but very legitimate reasons. Scandinavian countries seem to be leading the way, and Sweden and Finland in particular seem to me to be making very good progress in developing a nuclear waste facility, and with a basic thinking that is proved that can be built to be safe. So I hope that gives you a flavor of the nuclear waste disposal work. I'd now like to just move on to talk a little bit about more recent work, and that is underground coal gasification that we've been doing. Now, the approach, again, we've been doing numerical modeling work, developing our model to be able to describe this phenomenon. it's again, I should say, carried out very much in collaboration with other partners. In this case, this work has been largely funded by the European Union through their research funding coal and steel, and is led by a very strong partner in Poland that have a clean coal technology center. So underground coal gasification is, as the name says, the process of coal gasification, which is very well established, but carried out underground so that nothing is brought to the surface other than the gas itself. It is a complicated problem for sure. It has many similarities, strands of similarity to the work that I've already talked about, but the differences are very significant as well, and the main difference is the temperatures that are at play in this area. So the temperatures reach up to levels of 1,000 degrees centigrade here. Having said that, you can look at that picture there, and you sort of reminiscent a little bit of the picture I showed earlier, where there's many different processes: heat flow, gas flow, geochemical reactions in this case in the coal, post-solid flow, and soil skeleton deformation. So here's a sort of general picture of underground coal gasification, if you're not aware of it, where an injection well is drilled at one end of the coal stratum, the left-hand side of this slide as we look at it, and the production well is installed at a sensible distance away, and the coal is, as the name says, the coal is gasified in a systematic way, and works its way through that. The gasification works its way through that strata that you see there, and the production well removes the resulting gases that are generated. As part of this large European project, were sort of charged, if you like, and what we said we would want to do, and what we contracted to do through our research contracts, was to develop a numerical model to model this process of underground coal gasification to the best of our ability, with a view of looking at the environmental impacts and making sure that we, if you like, produce something that could be used with confidence, looking at the potential for environmental quality to be maintained of the surrounding areas and so on. We had experiments carried out, laboratory tests carried out. We are now, of course, talking about coal, not soils and rock. Well, it's a rock in its own way, but not the traditional geotechnical work. And this diagram simply shows you the sort of, the fact that there is, and there was in Poland, in the Central Mining Institute, a very well developed equipment set up in order to carry out experiments on underground coal gasification. The model development work that we carried out is illustrated here in general terms. Multi-phase and multi-component model based on porous medium approach. Primary variables of temperature, solids component, and gaseous components. Coal is composed of moisture, ash, and dry coal, and ash forms the main structure and remains intact. There's an awful lot to be said about coal and about various sort of grades of coal and the moisture content of coal and so on, and the material parameters that are needed to make these calculations work and so on. Forgive me, I'm just going to, in the time available, I'm just going to go straight over all of that, but I do want to acknowledge how important all of that is, and the variability of coal and so on, and how important that is. And I don't want to give you the impression that I consider that unimportant or anything like that. This is the experiment with hard coal, the ex situ large-scale UCG reactor experiments. This slide describes the work that was carried out on that front, and this experiment assembled and ignited, if you like, and recorded. And we then carried out simulations of that ex situ large-scale UCG reactor experiment. That's the lower diagram in there. And this gives you then some pictures really of the results that we achieved from that. Temperature results, the dry coal results, char, porosity and permeability. So that, I hope, gives you a flavor of that work. As far as the environmental considerations are concerned, these are the research questions of interest. They're all to do really with the flow, the creation of contaminants, and then the flow of those contaminants. So the gaseous and dissolved species flow and the reaction mechanism during the gasification process and the decommissioning stage. So we try to take into account the effects of high pressure UCG operation and cavity ash leaching, the effect of permeability and porosity induced by UCG on the contaminant transport, and the impact of regional groundwater flow and the persistence of contaminants. And in general, and we had, in traditional sort of European Union project terminology, we had model applications in selected study areas. One is shown here in South Wales in the United Kingdom. One is in the Silesia Basin in Poland, and one is in the Ruhr district in Germany. And so we carried out work on applying our models in those areas and looking at, these are the results for the South Wales coalfield, looking at degree of saturation, CO2 concentration, and temperature. These are diagrammatic, obviously, of the impact of UCG on those strata. And the main conclusions, I would say, from our work, which was a sort of, three-year project was that we developed the model, and we verified and validated it against available literature data on former UCG trials. My colleague, Dr. Gao, who worked closely with me and in fact, developed the model, would say that this part was the most difficult part, really, was the verification and the validation against available data. That's the part. Main conclusions of our work, of deep UCG work, the environmental issues were into consideration in a sensible way, shall we say. There was suggested that this wasn't the right thing to be doing at all, but it just the ground is a very good, if you like, a very good sort of barrier for some of this work. And then finally, I would like to say a few words about our latest work and our latest project, which is on carbon sequestration in coal. Now, this is quite timely. We're all aware of carbon sequestration requirements. Most people, I suppose, are most aware of the plans to put CO2 in abandoned gas fields or in saline aquifer type of locations. This is something different. This is putting it into abandoned, or putting into coal. The big advantage of using coal, and it's been looked at by numerous other organizations in the past, and I'm sure that many of them have been in the US, is that the CO2 is absorbed into the coal. So in essence, the thinking is, if you can get the CO2 into the coal, then it'll be bound in, it'll be tightly bound in, and in contrast to it, in other words, it'll be chemically absorbed into the coal, in contrast to physically sort of containing it in a depleted gas reservoir, for example. So if it's in a depleted gas reservoir, then there's obviously the residual then concerns, if you like, or considerations, probably a better word, that you need to be able to monitor it to be sure that it's where it is, and that there's no danger of escape, if you like. So that's the big positive for CO2 in coal. The price to be paid for that is that it is a considerably more difficult task, really, and the people that have looked at this in the past, and carried out full-scale experiments and so on, have had limited success, shall we say. So it's a live, real research area of interest, with a number of people sort of coming to the conclusion that it might not work, if I'm honest with you. So we're taking on it. We took on a bit of a challenge. Here, where I'm from, in Wales, in the UK, there is quite a large coal field, and I must admit, we did at the time think that maybe, given that we have also some big industry here, that we might be able to connect those two things together, and we might be able to do something of value to the region. That didn't prove to be the case, but that's for sort of politically related reasons. If you recall what I was saying earlier about that micro-macro interaction in the experiment at ACL on the bentonite, it's quite interesting and kindles similar thoughts when you look at CO2 uptake in coal. Because what happens is that if the CO2 is taken up by the coal, the matrix swells and causes the cleats, the main fractures, to then begin to close up, and it becomes more difficult to inject the CO2 in, as obviously as that happens, because the larger fractures are then themselves then starting to close. Similarities with bentonite. This is the project that we are currently working on. It is another one of these European Union funded projects, European Commission Research Fund for Coal and Steel. We coordinate it. We are very fortunate to have as partners GFZ from Germany, who are looking at the techno-economic side of this, CMI, Central Mining Institute from Silesia in Poland, and a mining company, Polska Group, PGG, also in Poland. Poland, the Silesia area, has very large coal reserves. It does still have some coal mines operating, and it is doing a lot of work on the post-mining possibilities for coal mines. So it's very interested in this particular area. It also has something that is particularly interesting if you're a researcher, and particularly valuable, of course. It has an in situ, it has a mine, basically an experimental mine. It's called the mine is called Barber, and it was established many years ago, largely at the time for for explosions, methane explosions in coal mines. But it's still there. It is it's maintained, and it is an active in situ test facility. So we have we've got an experiment ongoing there of gas injection and active monitoring system. We have we've been looking at a horizontal well system to pump the CO2 into the coal, and that has been achieved, and we are assessing the results and so on as I speak to you. So that's a couple of shots of the actual underground research laboratory in this case, compared to the underground research laboratories I showed you for nuclear waste disposal. This is of a different type, really, in the sense that it is far more shallow. It's about 35 meters below ground only, and that is significant. And that's the picture there of the seam on the right-hand side where the CO2 is being injected. This is the sort of static geological model of the Barbara mine. And you can see, I hope you can just about see where the coal is and where we will be hoping, or where we are injecting the coal. Maybe I should just say a little bit more about the Barbara mine. It's been in existence for a long time, and one of the things that's happened there is that it's been, because it's been very well used and very well examined, it has in many ways, the methane has in many ways already escaped from the coal. It's also at its, over decades previously, so to speak. So gas transportation, this is the modeling approach that we developed, and another colleague, Min Chen, who worked on this. The challenge here is to look a little bit more at the cleat networks, the coal matrix, and to accommodate all of that into the modeling work and the modeling approach. We, in order to get the CO2 absorbed into the coal, we're also kind of obviously quite interested in the internal surface area under which the CO2 will be absorbed. So the way that Min proposed, the approach that he's developed, is this development of a hybrid coupled geoporosity and discrete fracture model. I'm sure we've all over the years experienced the ups and downs of modeling fractured materials, and different permeabilities, obviously very large different permeabilities. Due to conductivity, contrast, and roles of fracture scales, where we've started with is looking at taking into account only the large fractures dominate the flow pattern, and these are required to be modeled explicitly by means of a discrete fracture model. Coal cleat network and coal matrix are modeled using a dual continuum approach called hybrid coupled dual porosity and discrete fracture model. And this is there to just to sort of remind me that, the work is pretty computationally intensive. So we've used a parallel computing approach, and this is a sort of schematic of the parallelization that we've been using, taking these various sections at a time. Distributions, the results of distribution of absorbed CO2 and CH4 concentrations, and then some results of the CO2 storage results that come out of the work that we've been doing. So what is that? And then some further results of predictions of how things should behave. So where does that all leaves us is that our modeling approach seems promising, but we are still in the relatively early stage of this research. What has become crucially important here in Europe. The UK was in, sorry to mention the dreaded Brexit word, but the UK was in the European Union when we were awarded this contract, so it is an EU contract. We were initially awarded the contract in effect as a sort of CO2 sequestration plus enhanced methane release from the coal. During the negotiation of the contract, the EU's Green Deal came into effect, where the European Commission was very, very concerned about methane escape and so on. We had to modify our contract during the contract negotiation stage. We were kind of lucky in a way because the Barbara mine had very low, had potentially it really exhausted itself of methane. So we were able to proceed on that basis. And now there is a sort of slight change of language at any rate in Europe that, after the invasion of Ukraine, that, maybe the release of the gas or the capture of the gas is, maybe going to be something that the authorities would be more interested in. The results we have found are very specific to the project that we worked on, that is relatively low level, not very deep coal seams of a particular nature. We're now beginning to think about a second full-scale experiment in a deep mine, working with our industrial partner. And as we take this forward, so the work so far is encouraging and is promising, and we're hoping that we'll be able to get support to continue this research. And I think at that point, I'll probably draw this presentation to a close. I hope that I do once again appreciate it's been fairly high level, and I hope that it's been of some interest to you. I really, really want to thank my colleagues in the GRC. There have been many of them over the years who have, as I said at the beginning, really done so much of the work and done so much of the nitty-gritty work. I want to thank our research funders, largely for me, the European Union in various shapes and forms, and the work from Bioatomic Energy of Canada, and our research partners, the organizations that, again, seem to me in some ways to do the hard work in doing all these very, very, very hard, difficult experiments to provide the results for us in the modeling community. Thank you very much indeed for listening. I'll leave it at that point. Thank you.